Hello everyone. So we'll discuss about we'll continue our discussion rather on fixed point and floating point formats. Why are we discussing this? Is because DSP processors they come with two variants: a fixed point processors and floating point processors. Let us see what's the deal with the typical representation of numbers, and then we will convert the numbers from integers to floating points. How do we represent floating point numbers? Then we will discuss about q notation, and then finally we'll go to the floating point representation. Okay, so here is a typical two's complement representation. So there is the options we have usually for representing numbers. Signed ones is sign magnitude representation. Sign magnitude means the first MSB is given for sign, the remaining bits indicate the magnitude. There is one's complement, then there is two's complement. One's complement is sort of confusing because zero can have two values, something like that. Two's complement is better, it gives a wider range. So here are the typical numbers. So you can see 0, the first bit indicates the sign. You can see this minus 4 here is additional number. You can see for 1, you can see 1's complement. Okay, so how do you get 2's complement? You get 1's complement of the number, then you add 1 and you end up getting 2's complement. Okay, so you can see the advantage of 2's complement. You get a minus 4 extra, which is not the deal with either sign magnitude or 1's complement representation. Okay, let us continue. Okay, so what can go wrong? What can possibly go wrong? So here are the two situations: 2 into minus 1. See, when you are allocating 3 bits, okay, so the numbers can be 0 1 1 on one side, or 1 1 1 on the other side. Let us revisit that particular let us let us revisit the previous chart what we had here. What is this? So we can have numbers from minus 4 to plus 3. Okay, we can have numbers from minus 4 to plus 3. So whenever we do this, 2 into minus 1 is going to be minus 2. That's cool. But 2 into minus 3 is going to give you a number minus 6, which is out of the range. And that's when we get a overflow. That's when we get a overflow. By the way, how do we do this particular thing? So we can see here 2 into minus 1, we went ahead straight away into the multiplication. Then afterwards, 2 bits were assumed to be sign extension. If at all it's a positive number, both will be 0 0. If it's a negative number, both will be 1 1, I guess. Okay, so here you can see the last two numbers were uh, okay. Since we are expecting the number to be a negative quantity, two's complement has been taken. Then afterward, these two numbers have been removed, and luckily, the answer was in the range. It was not the case for this particular thing: 2 into minus 3, giving you minus 6, whereas the maximum possible number that you can represent was minus 4. So there was a overflow. Okay, so now one thing is for sure: limited number of bits can cause overflow or underflow. Overflow is when the number what you get is larger than the maximum value that you can represent. Underflow is when the minimum number you get is smaller than the minimum value that you can represent, and we end up in a situation in such a case. So that's why. Okay, let us see. So increasing the number of bits seems to be a possible solution. Okay, increasing number of bits seems to be a possible solution. Anyway, let us see now how can we represent floating point numbers. That's what the topic is all about, right? Yes, very similar. Okay, so two's complement system fractional representation. So here what we'll assume, see, there is this decimal dot, and the typical representation has been given here. So negative numbers are indicated by a 1 in the MSP. Dot is assumed in between, or here it has been mentioned specifically. Okay, and say I have a number 0.1101, the number will be 2 to the power 0, 2 to the power, sorry, this is the dot. So this is 2 to the power minus 1 plus 2 to the power minus 2 plus 2 to the power minus 4. That's how it goes. Okay, that's how it goes. Okay, then okay, so here a few examples have been given, and this is the topic that we are much more interested in, something called as q notation, because now where is the decimal dot going to be? The decimal dot location actually decides the dynamic range. So q formats are usually used. So whenever a particular processors are to be designed, they come to a common agreement that this is the kind of notation that we are going to follow. Okay, so Q15 notation is where, say, in a 16-bit wide number, they assume that from this particular extreme point, the decimal dot is going to be here between the 16th and the 15th bit. That's what make it a Q15 notation. Then this MSB here will be representing the sign. So in this particular case, the maximum number that you can get, maximum possible number that you can get, so you can see, so it starts from zero point 0.5 plus 0.25 plus 0.2 0.125 and so on. So the maximum number you can get is 0.999 so and so, and the least possible number that you can get is -1. So you do not exactly get a +1, you get some number almost closer to 1. Okay, you get a number almost closer to 1. So that's a typical Q15 notation. So you'll find later that usually it's a Q15 notation that is mostly used. Okay, so implied binary point, as I told you. So if at all somebody says that is sticking to Q13 notation, it means that this particular implied point is going to be lying somewhere here. This part will be fractional part, this part will be the the exponential part, and exponent, right? Exponent or exponential. Okay, that's how the typical representation is going to be. Okay, so then, yes, let us continue. So how do we do this, by the way? So you can do these things on paper, but if at all a decimal value is given and you are asked to convert it into a Q15 notation using computer, then you better know what sort of algorithm you can go for. And see here they have given the method, and it is handy even on to be solved on notebooks. So what you do, you multiply the number, and the carry is preserved. Okay, the carries are preserved. The remaining whatever carry, the product, the fractional part is once again taken, again multiplied, the carry is 0, again multiplied, the carry is 0, right? We have done this particular thing once again in the classroom. And finally the number what you get is here, see, 1 0 point is because it's a positive number. Then afterwards all these values will be written from MSP to LSP. Okay, then, yes, so here there are certain representations of Q format for a positive as well as negative numbers. Okay, so what can go wrong, by the way? What can possibly go wrong? So there are certain issues here with Q format. Okay, so I expect you to go through this numerical examples. Okay, because since most of the, probably this is the somewhat better, relatively better unit in DSP. So you do not want to miss out on this numerical examples. You should exactly know a particular format actually and the representation. Okay, but what is the problem typically with the Q notation? Okay, the problem with Q notation is that the numbers are, the range is limited. As I said, we can represent from -1 to +1, not exactly +1, but there can be certain errors. If at all you want more, how much error, by the way? So you can see in this particular number, what was it? It's 0.560123, whatever we took. Okay, we ended up making certain error here. There was a very small error which we had to let go. Not exactly this one, but if at all I take this particular sequence itself and then I do this particular thing, 2 to the power -1 plus 2 to the power -5 plus 2 to the power -6 -7 and so on, I do not exactly get this particular number. I get an error of order maybe 10 to the power -15 for this magnitude. Anything lesser than this, all those numbers will be neglected. So approximation errors are going to occur. If at all you want your number to be much more accurate, then you have to do is you can go for um, if at all I go for Q13 notation or a Q12 notation, I can represent more positive numbers, but then it's going to give me approximation errors for smaller numbers. Okay, the dynamic range may be increased, but then I may not be having accurate numbers. So in such case, we may have to go for something like a cube 31 notation. You may have to go for a cube 31 notation. Similarly, if at all you are going for a multiplication, if at all you multiply two numbers, then again, since earlier we saw so two 3-bit numbers we multiplied, ended up getting something 6-bit, right? At least to hold. Then afterwards we moved the number to the right side and we got the 3-bit number. But then temporarily to hold the value, we need a larger bit width. So you may have to go for 31 format. Okay. So, and what are the problems, by the way? If at all your number is more than 1, now suppose I add a zero point 0.6 plus zero point 0.6 in a Q15 notation, the number is always going to be larger than the maximum number that a Q15 notation can hold, which is not little less than 1, right? In such case, overflow is going to occur. So if at all I subtract zero point 0.6 from subtracting two numbers, so minus zero point 0.6 and minus zero point 0.6, if at all I subtract zero point 0.6 from minus zero point 0.6, then I get a number less than minus 1. There also I will get something, we call it as underflow. So these are the problems that Q notation can have. But anyway, one good thing is uh, using the conventional processors, using the normal bits only, fractional values, both positive and negative, can be represented but using Q notation. Problem is, on one side, if at all you are going for something like Q6 or Q3 notation, you can represent a larger dynamic range, but then you lose on the accuracy. If at all you are into accuracy, then you are limited by the maximum and minimum numbers that you can represent. Okay. So okay, what other options, by the way, do we have? Okay, if Q notation is something like that, if at all I want to go for a larger range, if at all you want to go for larger numbers, then you will have to go for floating point format. Okay, then you have to go for floating point format. So what's a typical floating point format? So when you say floating point format, then the whole burden is on the a programmer. Okay, it's a programmer's burden. Okay, let us see how things go. Okay, depends on the kind of processor you have. If at all you have a processor that will stick to the Q notation, then it's a programmer's burden to convert a floating point format to a Q notation, and vice versa in case you are having a floating point processor. Anyway, this is the notation for a typical floating point. We will come to a specific standard IEEE notation later. So what is it like? Say here it is. X is given by m dot e to the m multiplied by, okay, e to the power 2 to the power e. Okay. So see, here is a format given. Okay. So see, in this particular case, 12 bits have been assigned for mantissa and 4 bits have been assigned for exponent. Okay, so you have to come to a common agreement. Okay, what is going to be what? Okay, what's going to be what? And can you give an example, by the way? Let us see, in the next page. Okay, yes, here there is a range. Okay, okay. So something like this. Okay, you can see here uh, there are some numbers given. So, and the author is asking us to convert each of the following decimal numbers into floating point format. Okay. So the first number is given as 0.160123. So how are you going to do this particular thing? How are you going to do this particular thing? So which is the format that we have been asked? So you can see 4 1 for the exponent, remaining for the mantissa. Okay, 4 for the exponent, remaining for the mantissa is what has been asked. Okay. There, the number we are talking about, this is the format given. So here you can see 1 2 3 0 1 2 3 4. So there is a decimal dot expected after 11 bits. Okay, binary dot expected after 11 bits. So we will call this as a Q11 notation, at least for this particular segment, and the remaining part will go for exponent. Okay, exponent in 2's complement format. So now let us go and see this numerical. So number, this can as it is be represented in the particular format which was given in this particular figure that we saw just now. But then the approach used here is has changed a little bit thing, represent as 2 to the power minus 2. Okay, now suppose say I happen to have say 10.348, and I want to represent this particular thing say in 1.0348. How am I going to do it? If at all I want to represent it like this, then maybe I will have to multiply it by 10 to the power 1, right? Or say I want to represent this particular number as 0. Say 0.10348. If at all I want to do this particular thing, then maybe I will have to multiply by 10 to the power minus 2, right? I will have to multiply by 10 to the power minus 2. So similarly, in this particular case, the number whatever that has been given has been divided here by 2 to the power minus 2 to get an exponent of minus 2. So the exponents will occupy first 4 bits, and then the mantissa, then we'll have the remaining bits. So that leaves us with this particular number. So once you get this particular number, we'll multiply it by 2, get the number on the right side, right? As you saw in the previous table, pick on the MSB, pick on the MSB, then take the remainder, again multiplied by 2, pick on MSB, and so, and we end up getting this particular thing. So the exponent value is minus 2. So here you can see minus 2 has been represented here in this first 4 bits, and then this exponent has been taken up here. So you can see 0.640492. Okay, so 1110 is what is representing minus 2, the exponential part, whereas 0.06, you can see this number could have been negative or this number could have been positive. So since the number is a positive number, 0, then the remaining bits, as we have done earlier, 0.64 into 2, it gives MSB of 1, the remaining 0.4, then it gives 0, and so and so. The remaining 12 bits, okay, they will adhere to Q11 notation. Okay, they will adhere to Q11 notation with this particular bit indicating the sign of the mantissa, whereas this particular bit indicates the sign of the exponent. Okay. So now let us see in the same case. See, the number could have been again represented, kept as it is in 0. Then this would have been all zeros here. Okay, this would have been all 0, 0, 0, 0. Then the number as it is could have been represented again with a 0. But then it could have been minus 1, it could have been minus 2, it could have been minus 3 also, since nothing specific was asked. So this way. Now let us see what about the second number. What about this particular number? Let us see what will be the approach here for this particular number. So you can see we can still represent this particular number. Earlier in the normal Q15 notation, we were restricted to use only numbers like from -1 to +1. Here you can see we can represent larger numbers. Okay, so let us see what is the approach here. So for this particular case, 2 to the power minus 5 has been 2 to the power 5 has been selected to get a number. So you have to get this particular part, the this particular value has to be less than 1. That is the rule. You have to divide it by such a number so that it part turns out to be fraction. So the previous number doesn't actually justify the need for the division. This number actually justifies the need for the division. Once that is done, 2 to the power 5. See, the number is still negative, but the exponent is positive. So exponent is positive. That's where this 0.101 had come in. And for this particular thing, since this was negative, so once you got the entire value converted, 2's complement has been taken. 2's complement has been taken. So this part here represent the positive exponent 5 whereas this part here represents the 2's complement of the fractional part, which was converted using the earlier division thing. Okay. In once again the q notation. Okay, sticking to the q11 notation. So then what about floating point arithmetic? By the way, what we just studied was floating point representation. How is the arithmetic? How is the arithmetic? Okay, so what is the usual decimal floating point arithmetic? How is the typical decimal floating point arithmetic? Now suppose I have to do say 10.23 plus uh, 0. Say 002. So what do we do? So we'll make sure that the decimal dots are aligned, right? Then see here 0.002. This is how we do it. Okay, so now with minimum number of fields at our disposal, we have to do something like that here also. So the rule is if at all you are trying to perform the sum of two numbers using this particular representation, so what happens is exponents are added. Okay, the exponents are added, and they should be adjusted also. You can see this is the formula to be used depending on if at all the first exponent is larger, second exponent is smaller, then you have to stick to the first formula. First exponent is smaller compared to the second exponential, then you have to stick to the second formula. Let us see an example. Okay, how actually are we going to do this particular thing? Now say I have to add two numbers, say 10 into 10 to the power 3 plus 2 into 10 to the power 5. Okay, how are you going to do this particular thing? So maybe you will adjust this particular number 10 into 10 to the power 3. You want to make this as a power of 5, right? So how are you going to do it? You will divide this particular number by 100 to make it zero point 0.1, right? Make it zero point 0.1. So you can see that particular action is being represented here by this 2 into minus of e2 minus e1. So 10 divided by 10 to the power minus of 5 minus 3, that gives this particular thing. Then when the decimal dot is adjusted, then you go ahead with the addition. Then afterwards the final 10 to the power minus 3 is appended. Okay, so that is the action what you do. So whenever you are trying to do this floating point addition, the exponents are need to be manipulated. So same is the case with binary number also. So whenever you are trying to do multiplication of two normalized floating point numbers, in whereas in for this particular case, what do you do? The matrices are multiplied, whereas the exponents are added, right? Suppose you have to multiply e to the power minus 10 with the e to the power minus 13. What do you do? So usually the exponents, they are added, right? It is something similar. Okay. So action is something similar. Okay. Okay, so yeah, same thing, multiplication and addition. So here are numericals examples that have been given. I can see here, see 10 to the power 2 to the power minus 2 and minus 5 are there. So this particular number has been adjusted, okay, to the larger numbers value to get this particular number by the multiplication. Okay, so this particular number is indicated and is indicated by this particular step here. Let me go back uh, here. So this was the case, okay, this was the case, and accordingly, so the number which has been indicated is after doing these two steps and adding to the second number, then finally the whole multiplication by the exponent. Okay, so I cannot explain this much, you have to work it out on your own. Okay, you have to work it out on your own. Okay. So what can go wrong? By the way, here also there can be overflows or there can be underflows. Okay, in the cases there can be overflows and there can be underflows in this particular cases. Now let us talk about the IEEE format. Okay, so we spoke till now about two formats: the q notation, q15 notation, which is bound by a very limited dynamic range from -1 to +1. Then we saw the normal floating point representation, which gives us the freedom to change the minimum and maximum possible values that we can represent. But then you saw how complicated it is for the addition and multiplication. So now you might be realizing how good it is to have a fixed point processor or a floating point processor. When you say a floating point processor, the whole complications in multiplication and addition will be taken care by the processor, but the processor is going to be very complicated, it's going to be costly. Whereas if at all you opt a fixed point processor, it becomes a programmer's burden to do all those adjustment by adhering to the q notation. Okay, by adhering to the q notation. So IEEE specifies a particular notation called as single precision and double precision and something called as extended precision. This one here is a single precision format which is for 32 bit. Okay, single precision format for 32 bit. Here the representation is sort of tricky. Okay, so you can see minus 1 to the power sign plus 1 dot fraction multiplied by 2 to the power, see here, 2 to the power e minus 127. So e here is 128. So it's sort of a biased exponent. Okay, it's a sort of biased exponent. It's not what we saw earlier. Okay, it's very unlikely to what we saw earlier, but IEEE follows this, so we also have to follow this particular notation. Okay. Even the ICs, whatever we are going to see later, they will also not adapt to this. So every different IC manufacturer, they go for different one, but they will mention. So it's up to the programmer to make sure that proper calculations are achieved. So here is a format for single precision. Single precision again is a arrangement thing. If at all you want a larger precision number, okay, so here is a simple numerical given. Convert the following IEEE single precision format. So you can see after dot and 0 and 1, he has left it. So assumption is that the total width is 32 bits. You can see the tricky part. Okay, it's a biased one. 2 to the power 7 should be taken into consideration so that this number, whatever he got here. Okay, so you can see exponent, first number. What is this? 2 to the power 7, right? This particular number is 2 to the power 7. First number is the sign, and then remaining numbers are 0. So 128 minus 127, 2 into, okay, this is the tricky part. Okay, this one was easy. 2 to the power 1.25, 2 to the power 0 and 2 to the power 1. This was sort of okay. This is where things were tricky, and you achieve getting the thing. So be clear on the actual format. So the trick in this particular chapter, I think, is not to get confused between q notation, the floating point representation, and the IEEE format. Then there is double precision. So as I said, the word is precision. Precision is the ability to represent maybe the smallest of the numbers without much deviating from actual value. Okay, so when you say double precision, what has changed, by the way, in double precision? Shall we see once again what has changed in the double precision? A single precision format had exponents allocated with how many values from 22 to 30, and the fraction part from 0 to 22, total 23 bits. Whereas what's the difference here in double precision? The fraction part is 0 to 31. So this is totally 64 bit representation. That gives, again, you can see there is larger exponent and larger fraction part. Okay, larger exponent and larger fraction part, which again gives you a larger range. Okay, so here also you can see, if at all you are asked for a conversion, this is the formula that you are supposed to adhere to. Okay. So since, but if at all you are using the ICs, whatever the processor you are comes with a 32-bit registers maximum, then you get this freedom of storing it in a pair of register by storing a half of the thing in even register, half of the thing in odd register, if at all you want to do it. So when IEEE specifies format, they take care of these things also. So see here, numerical has been given for double precision floating point format also. Okay, so now let us talk about the two processors. We will talk about one TMS processor, which is a fixed point DSP processor, and one floating point DSP processor. Okay, so I will continue in the next video.